Imagine a world where no one dies waiting for an organ transplant. Right now, 17 people lose their lives every single day because there aren't enough organs to go around. Well, what if we could simply print new ones? Not with plastic, but with living cells, customized for each patient, eliminating the risk of rejection. This isn't science fiction anymore. It's the cutting edge of regenerative medicine. Everything is a system. In grade 11, we're exploring how complex biological and engineering challenges, like bioprinting human organs, can be understood and solved by breaking them down into interconnected parts. Meet Dr. Iris Thorne, a lead biomedical engineer at the National Bioprinting Institute. He explains that bioprinting uses specialized three-dimensional printers to deposit living cells, rather than plastic, layer by precise layer. The biggest challenge? Vascularization. Engineered tissues need a vast network of tiny blood vessels, just like made of organs, to deliver oxygen and nutrients to every cell. Without it, the cells in the construct's interior quickly die, preventing the tissue from ever becoming functional. Another hurdle is sourcing billions of cells and ensuring they don't trigger an immune response from the patient. To understand how we might print a human organ, we need to look at its key components. We have two external inputs: print resolution, which is how precisely the printer places cells, and nutrient diffusion limit, the maximum distance cells can survive from a blood supply. Our 5 internal outputs are cell viability rate, vascularization depth, scaffold degrading rate, immune compatibility, and functional maturation. Each of these plays a critical role in the success of a bioprinted organ. Let's look at the relationships between these components. Print resolution has a complex effect on cell viability rate. While precision helps, extremely high resolution can damage cells, showing a positive relationship up to an optimum, then negative. A positive relationship exists between vascularization depth and functional maturation. More blood flow means cells get the nutrients they need to mature and function. Conversely, the nutrient diffusion limit has a negative relationship with vascularization depth, as it physically restricts how far apart blood vessels can be, forcing denser networks for thicker tissues. Finally, scaffold degradation rate has a nonlinear relationship with functional maturation. The scaffold must degrade at just the right speed. Too fast means collapse. Too slow prevents remodeling, both hindering function. Build your bioprinting model. What if we increase print resolution to its absolute maximum? How does that impact cell viability and ultimately functional maturation? Or, how can we balance the scaffold degradation rate to ensure the tissue doesn't collapse, but still remodels effectively for a functional organ? Careers in this field are growing rapidly. Biomedical engineers, earning $80,000 to $150,000 a year, design the bioprinting systems and tissue constructs themselves. Regenerative medicine scientists, with salaries from $90,000 to $170,000 annually, develop new techniques for growing replacement tissues and organs. Everything is a system. Model it, build it, simulate it, understand it. Visit ModelIt K12.com.